So for the benefit of those persons. Okay, so I take it that you guys can hear me out there, or how many of you are out there? Oh, yes. Okay, so Mr. Sullivan and Mr. Donnelly, can you hear me now?
Yes,
Okay.
I can hear you.
Yeah, sorry about that. You missed some earlier comments I made, but you can catch up on it on the video that I'm going to post because I'm recording this lecture right now. All right, so as I was saying, we will be talking about Hess's law of constant heat summation. And basically this law, as I was saying earlier, is a consequence of the law of conservation of energy, right? And if you remember, that law says that energy cannot be created nor destroyed, but can be converted from one form to another. So how does this apply to chemical reactions? Well, it turns out that in practice, it is very difficult, if not impossible, to carry out some reactions as it is written. You know, you can write down an equation, but when you try to design an experiment to carry the reaction, it's oftentimes, in some cases, very difficult or even impossible, right? However, if we can determine the enthalpy changes of other related reactions, then we can determine the enthalpy change of the reaction which we cannot perform, all right? So just to give you a simple example, let's say you have this reaction here, the reaction between carbon and oxygen to form carbon monoxide. Now, this is a very difficult reaction to actually perform, right? And the main reason why is that the carbon monoxide itself is very reactive. It will react with any oxygen that's present to form carbon dioxide, right? So, so that's basically what is stated here. If we burn 1 mole of carbon and half a mole of oxygen, both carbon and carbon dioxide would be more likely produced, and that's because the carbon monoxide will itself react with oxygen to form carbon dioxide. And not only that, but as stated here, some carbon, the original carbon here, might be left over, all right? So how do you determine the enthalpy change for this reaction? Well, we need to remind ourselves of the fact that enthalpy change is a state function. And therefore, what does that mean? That means that the enthalpy change of a reaction is the same whether the reaction is carried out in one step or through several steps, right? So what this is saying is that if you can carry out a reaction in one go, right, and you determine the enthalpy change for that reaction, you can also, and let's say you can also carry out that same reaction through more than one step. It doesn't matter if you take one step or more than one step, the enthalpy change for the reaction would still remain the same, whatever it is, all right? And it is on that basis that we can exploit that particular fact in order to determine the enthalpy change of a reaction, which we may not be able to perform in practice. So this brings us to Hess's law. And Hess's law basically says that if an equation can be expressed as a sum of 2 or more equations, the enthalpy change for the desired equation is a sum of the enthalpy changes of the other equations, all right? And you might see it expressed differently in other textbooks, right? But that's basically what Hess's law is saying. What Hess's law is saying is that if you have one equation that can be expressed as a sum of 2 equations, then the enthalpy change of that one equation will be the sum of the enthalpy changes of the equations that you add up to get that one equation. So let me just use a simple hypothetical example to illustrate this. So let me go to this right here. Oh, let me get my stylus. Okay, so let's say we have the possibility of reaction A going to C, right? And let's say it is possible for you to go from A to an intermediate B, and then from B to C, right? So there are 2 ways of going from A to C, either the direct route or through an intermediate, right? So let's say the enthalpy change for going from A to C is delta H3, and let's say the enthalpy change for going from A to B is delta H1, and let's say that the enthalpy change here going from B to C is delta H2. Then what Hess's law is saying is that delta H3 is equal to delta H1 plus delta H2. That's basically what Hess's law is saying. So basically what they're saying here, or what Hess's law is saying, is that it doesn't matter if you go from A to C directly, or you go from A to C through an intermediate B, the enthalpy change will be the same, right? And therefore, let's say, for example, practically speaking, you're not able to determine this experimentally, but let's say you're able to determine this value and this value, then you can use this equation to solve for delta H2, all right? So that's a practical aspect of using Hess's law, all right? Okay, so let me go back to the PowerPoint here, and let's see what we have next. Okay, so this is the example of carbon reacting with oxygen. Let's start off with that, right? So basically, if you remember, we said that going from carbon plus half a mole of oxygen to form carbon monoxide, that's very difficult to perform in practice for the reasons I mentioned before, right? So let's say we need to determine that. Now we can go from carbon and oxygen, go directly to carbon dioxide, and we can also do the reaction where carbon monoxide react with half a mole of oxygen to form carbon dioxide, right? So according to Hess's law, this step, the enthalpy change here, plus the enthalpy change here, will be equal to the enthalpy change here, right? So basically, we can do a simple arithmetic type solution. We can say that delta HA plus delta HB is equal to delta HC. So therefore, to find delta HA, that would be equal to delta HC minus delta HB, all right? So all we have to do is put the values in. Delta HC is minus 393.5 kilojoules. And let me put that in parentheses. And then we subtract from that delta HB, which is minus 283.0 kilojoules. And that's it. All we have to do is the math, and that will give us the value of delta HA. All right, so without doing the reaction itself, but knowing the values of other related equations, we can calculate the enthalpy change of the reaction, which, as I said before, for reasons that I mentioned, would be difficult to determine experimentally. All right, so that's basically what Hess's law is all about. Now, let's look at this example here. Now, this example is basically a typical Hess's law question that you could get in your, well, not this test coming up, but the next test, all right? The question gives you these three equations, right? And the first equation is what the question is asking for you to do. You're to determine the enthalpy change of this reaction right here based on the information provided with these equations along with the enthalpy changes given, all right? Now, since I'm going to need some space for this, I'm going to copy and paste this. Let me copy. In fact, you know, I don't even need to copy the top part. I'm just going to copy these equations here. Control C. And then let me use Word. Word seems to be a more convenient application to use. I thought I already had a Word document open already. Let me see. Okay. And let me close this. Close. Okay, what's going on here? All right, so let me paste this here. All right, so basically, this is what we need to find based on the information provided by the other three equations. Let me make this a bit larger. Okay, so how do we solve this based on the information provided? Okay, so whenever you're given a typical problem of this type, what you need to do is compare each equation to the original equation for which you're trying to find delta H. So for example, if you compare equation B to equation A, all right, you'll see that you have carbon on this side here and carbon on this side here, right? So what I would do to this equation here is that I would multiply this equation, the entire equation, by 2. And the reason why is because I have a coefficient of right here in the equation for which you're trying to find delta H, right? Now, key thing you need to remember is that if you multiply this equation by 2, that means that the delta H value here must be multiplied by 2 as well, right? So I'm going to write down what results when you multiply that equation by 2. You're going to get 2 carbon solid. And by the way, whenever you're doing these equations, these problems, make sure that you include the state symbol, right? Because in some problems, the state symbols can change and that can make a difference, all right? So 2 carbon solid plus 2 O2 gas to give 2 CO2 gas. Whoops, 2 CO2 gas. And the resulting delta H value as a result of that is 2 times minus 393.5 kilojoules. All right. Okay. So that's what we do to equation B. So now we're going to look at comparing equation C to equation A. And what do we notice? In that case, we notice that we have C2H4 here on the left, but in this equation here, it's on the right. So what I'm going to do to this equation is that I'm going to switch it. In other words, I'm going to make the reactants the products and the products the reactants. But if I do that, that means that the sign is going to change from negative to positive. All right. So when I'm just going to write switch here. Switch. Okay, so when I do that, I'm going to end up with 2 CO2 gas plus 2 H2O liquid on the left. And then on the right side of the arrow, I'm going to put C2H4 gas plus 3 O2 gas. And therefore, delta H for this is going to be equal to positive 141.0.9 kilojoules. All right. And that's basically what you do to equation C. All right. Now, we get to equation D. So when we compare equation D to the first equation for which you're trying to find delta H, you'll notice that you have 2 H2 here and you have 1 here. So what do you think we should do to this equation? Multiply the entire equation by 2. Exactly. So you're going to multiply this equation by 2. So you're going to end up with 2 H2O, I'm sorry, H2 gas, plus O2 gas. And then on the product side, you're going to have 2 H2O liquid. All right. And therefore, what is the delta H value for this? Exactly. So 2 times minus 285.8 kilojoules. All right. Okay. So now that we have done that, the next step is that we need to add these equations. Scroll down a bit. Now, remember, whenever you're adding equations, remember we cancel out those items that are common to both sides. All right. So I want you to look at these 3 equations that we just wrote down and figure out what particular formulas will be canceling out. Remember, identical items will be canceling out on both sides. So what will cancel out in this case? Okay, so these 2 water molecules here would cancel out with those 2 here. Anything else?
The 2 CO2s.
Okay, somebody in Zoom says the 2 carbon dioxides here and here. Anything else? All the oxygens will cancel out as well, because on this side we have 2 plus 1, 3, which will cancel out with the 3 oxygens here, right? So what are we left with? There's nothing else that will cancel out. So we'll be left with what? 2 carbon solid plus 2 H2 gas. Those are the items on the left side of the equation. And then on the right side of the equation, you're going to have C2H4 gas. And if you look at this closely, you'll see that this is the same thing as the equation for which we're trying to find delta H. Same equation. Exactly. That's how you have to work towards getting the equation that you're trying to find the delta H value from. So what does that mean for the delta H value for this equation? That delta H value here would be the sum of all of these right here. All right. So Let's do the number crunching. And I think I made an error here. This should be, this here should be 393. Okay, so it's going to be 393.5 negative times 2. And then I'm going to add to that 1410.9. And then I'm going to add to that 2 times negative 285.8. And according to my calculations, and please correct me if I'm wrong, but this is what I got. I got 52.3 kilojoules. All right. So that's a typical Hess's law type question that you can expect to get. In fact, I give you guys assignment number 6, right? Okay, good. So you're going to see examples of that in that assignment. All right. Okay, any questions about this particular example? Any questions? Any questions? Okay, so let's see, what is next? Okay, now let's talk about standard enthalpies of formation. Now, by definition, the enthalpy change of any reaction would be equal to the total enthalpy of the products minus the total enthalpy of the reactants. But there's one problem with actually utilizing this equation, and that is that there is absolutely no way of determining the enthalpy total of a product and that of a reactant, all right? So how do we determine the delta H value of a reaction by calculation? Well, since we cannot determine, or since we cannot know the absolute values of enthalpy, what we'd have to do is use instead a relative scale. So basically what was done by the powers that be, they decided that, okay, we're going to adopt a standard for the purposes of measuring enthalpy values and other thermodynamic values, which some of you will meet in Chem 2, right? And basically what they have decided is that we determine some standard conditions, one of which would be 1 atmosphere pressure, and the other would be that the temperature would be 25 degrees Celsius. Now, please do not confuse these standard conditions with STP that we talked about in chapter 5. STP relates to gases, right? Standard temperature being 0 degrees Celsius or 273 Kelvin, and standard pressure being 1 atmosphere. In the case of measuring enthalpies, the standard conditions would be 1 atmosphere, which is in common with STP, but the other condition is that the temperature is 25 degrees Celsius, all right? So now, based on that, we can talk about measuring what is called the standard enthalpy change, and that is represented by this symbol right here. So it's delta H, which we met before, but there's a small o or 0 written as a superscript, right? So whenever you see this symbol here, you should understand that the delta H measurements are made under the standard conditions that we talked about earlier, right? Temperature being 25 degrees Celsius, and the pressure is 1 atmosphere, right? So that is basically the standard enthalpy change symbol, right? And then now another term I need to talk about is what we call the standard enthalpy of formation, all right? And the symbol for that is the same as I mentioned here, excepting that you have an F down here as a superscript. So therefore, that's a bit different. And what this refers to, as stated here, is that this represents the enthalpy change when 1 mole of a substance is formed from its elements in their standard states under standard conditions, all right? So this is what is used for calculations of enthalpy changes, the standard enthalpy of formation, all right? So for example, let me go back to my writing pad right here. So let's say, for example, we're talking about measuring the, how should I put this? The standard enthalpy of formation of H2O. Liquid, right? Well, what we're talking about here is the enthalpy change that occurs when this reaction takes place, all right? Because the definition says the standard enthalpy of formation is referring to 1 mole of water being formed in this case. So therefore, whenever you're writing down the formation of 1 mole of water from its elements, you have to ensure that the coefficient here is 1, right? And you balance the rest of the equation based on that. So therefore, this would be the equation for which the enthalpy change of formation is, whatever that value is. And that can be, of course, measured. In fact, there are tables that have been put together, one of which I have made available in Canvas. Let me just show you where that is. Let me go to, oops. Okay, so let me go to files. So this table is what you'll be using when you're asked to calculate the enthalpy of formation of, or actually the standard enthalpy of reaction based on the enthalpy of formation. So thermodynamic data, that's the name of the file. And if you download it, it's 8 pages long. But so this is what it looks like. Now, for us, for this course, we will only be using the values here, right? For those of you who plan to do general chemistry 2, then you'll be using these two values in the second and third row here, or columns, I should say. But the values that we'll be using here are these values here. So these are this enthalpy, the standard enthalpy of formation of these substances here, right? And one thing I want to point out here is that if you look at this table, you'll notice that when it comes to elements that exist naturally under standard conditions, the enthalpy of formation is basically assumed to be 0. All right? So I'm talking about, for example, aluminum. What else? Arsenic, barium, boron, all these elements by themselves, bromine, calcium, their enthalpy of formation is 0. And if you think about the definition, that makes sense. Because if you remember, the definition says the enthalpy of formation is the enthalpy change when an element is formed from its elements. But for the elements themselves, they're formed from their elements. So therefore, there's no change. So therefore, the enthalpy of formation is 0 for elements that exist in their natural state under the conditions that I mentioned earlier. All right. So this table you'll have access to doing your tests. So get familiar with this particular table when it comes to doing enthalpy changes under standard conditions calculations. Okay, so let me go back to the PowerPoint here. Let's see what we have here in the next slide. Okay, so here's another example of enthalpy of formation under standard conditions. In this case, we're talking about the formation of this compound, which is known as methanol. So basically, if you want to write down the equation for the formation of 1 mole of methanol, this is the equation right here. You'll notice again that the coefficient of methanol is set at 1, and you basically balance everything else based on that. And it turns out that this value here, the enthalpy of formation, based on this equation, has been determined to be equal to minus 238.7 kilojoules under the standard conditions, all right? So that's basically what enthalpy of formation is all about. Okay, so we treat these values as though they're absolute enthalpy values, and therefore we can use them to do certain calculations. And there's a question being asked here, which I dealt with already. It's asked, what is the enthalpy of formation of an element under standard conditions? As I said before, that's 0, all right? Oxygen, nitrogen, barium, calcium, whatever, all right? And that's because the reactants will be the same as the products in a hypothetical reaction where 1 mole of the product is formed. Okay, so how do we calculate the enthalpies of reactions under standard conditions using these values, the values that I showed you in the table? It comes down to basically using this equation here. Now, this might seem a bit complicated, but it's not really. Basically, what this is telling you is that the enthalpy of reaction under standard conditions would be equal to the sum of the standard enthalpy of formation of the products minus the sum of the standard enthalpy of formation of the reactants. Now, I don't know if you're familiar with this symbol here. It's the Greek letter sigma, uppercase sigma. I think I remember when I was in undergrad, this symbol is used a lot in math, or I should say more specifically, statistics, right? It means sum of, right? And this symbol here, the nu with the P here, and the nu with the R, P for products, R for reactants, it stands for the coefficient of the different substances involved in the reaction, all right? So I'm going to show you how this works. But remember, basically, to calculate the enthalpy of reaction, it's pretty much sum of the enthalpy, standard enthalpies of the products minus those of the reactants, all right? And this is much easier to use than Hess's law, even though Hess's law can be used in these problems, but it's much easier to use these in order to solve problems of the type we're going to look at. So here is one example. And again, I'm going to need your help with these examples. I need at least one of you to pull up the table I just showed you, right? With the standard enthalpy values for different substances, because I need you to tell me the values of certain substances involved in this problem that I'm about to get into. Okay, so this is the question here. It's talking about this mixture of carbon monoxide and hydrogen, which is produced in this reaction. And it says you're going to use the standard enthalpy formation values from table 16.2 to calculate the standard enthalpy change for this reaction. So let me just write down, get the pen function first, working. Okay, so let me just write down how you'd set this up. So basically, as I said before, it is the sum of the enthalpy of the products, standard minus the standard sum of the enthalpy of the reactants. So these are the products and these are the reactants, all right? So basically, delta H standard would be equal to 4 times the enthalpy of formation standard of carbon monoxide gas plus 8 times the enthalpy of formation of hydrogen gas, H2 gas. Okay, so I'm going to put that in square parentheses here to isolate it from the values or the terms for the reactants. So these are basically the terms for the products, right? So for the reactants, we have 3 as a coefficient here. So 3 times the coefficient, times the enthalpy of formation of methane, which is CH4 gas, plus 2 times the enthalpy of formation of H2O liquid, and then plus the enthalpy of formation standard of CO2 gas. All right? Okay, so those are the terms, right? These are the terms for the products. These are the terms for the reactants. So all we have to do now is consult the table and look up the values for carbon monoxide, hydrogen, which is going to be 0 because remember, hydrogen is an element by itself. Remember what I said before, right? So you don't even need to look up that one. You're going to look up the value for CH4, for H2O liquid, and for CO2 gas. And please pay attention to the state symbols because, for example, the value for H2O liquid is different from the value for H2O gas. So make sure you pay attention to the state symbols. Okay, so who has the table pulled up? Anybody? Okay, so what's the value for the enthalpy of formation standard for carbon monoxide? Negative 110.553. Okay, kilojoules. Okay. And then what? Oh, as I said before, hydrogen is 0, so I'm just going to put 0 here. Okay, so that takes care of the products. Let's scroll down here a bit. I need some more space. Let me just draw a line here to avoid confusion. Okay, what about the reactants? Starting with methane. Three times the value for methane. What's the value for methane? CH4. Oh, I forgot to mention something. You might find methane a bit difficult to find initially, but if you scroll down, let me see if I can find that table again. if you scroll down to, I think, the last page or the last two pages, you see a special section for organic compounds. So I'm talking about this right here. And if you look at this here, you see that the enthalpy of formation for methane is right here. Right? I think this is the second to last page. All right, so there's a special section in this particular table for organic compounds. So that's minus 74.81. So I'm going to put that here, minus 74.81 kilojoules. Okay, and then now I'm going to add to that 2 times the enthalpy of water. So 2 times the enthalpy of formation of water. So can you tell me what that value is? H2O liquid, by the way, not gas. $285 point what? $83, all right. So if I get this wrong, blame her, all right? And then for carbon dioxide, well, it's only one of them, so CO2 gas. Okay, so that's it. And then all you have to do is do the math, all right? And what I like to do is work out one section first, like the products first. So that would be 4 times 110.53. Okay, so this part here works out to be equal to 0.12, and this should be negative, and this will be kilojoules. All right, and then on the other side, you're going to have 3 times minus 74.81. And then I'm going to add to that 2 times minus 285.83. And then I'm going to add to that, or maybe I should just subtract 393.5. Okay, now this side here, I got minus 1,189.59 kilojoules. And then I'm just going to do okay, so according to my calculations, this works out to be 747.47 kilojoules. And that's it. That's basically how that is done. All right. You got something else? You look puzzled. Okay. And please feel free to correct me if I'm wrong, because sometimes I will make some mistakes when doing these arithmetic type situations. All right. So, any questions about this? Any questions? Any questions? All right. Now what I'm going to do is go back to the PowerPoint here. There's another problem here, and I'm going to leave you to try this on your own, right? I won't do it today. But if you have any problems while doing this, let me know. But let me try to explain what this question is all about. This example is all about. They gave you this equation, but the difference between this problem and this problem is that here you're trying to find delta H. Here they gave you delta H. All right? And what you're trying to find is the enthalpy of formation standard for this compound, which is known as isopropyl alcohol. All right? So all these values you can look up in the tables, right? Well, oxygen is going to be 0 because, again, oxygen is an element by itself, exists as O2 naturally. So therefore, this will be 0. So basically, just to give you a hint as to how to approach this, basically what you're going to do is find the values for carbon dioxide and for water, add them up on this side, and then that minus the unknown is going to give you this. You see what I'm saying? You find the total sum of the enthalpies of carbon dioxide and water, just like we did earlier. And then we're going to subtract from that this unknown, and it's 2 times that unknown, by the way, because of the 2 here, and that will be equal to that, and then you can solve for the unknown based on that. So that should help you in terms of solving that particular problem, all right? Okay, so based on what we have done so far, because this is actually the end of this chapter. So based on what we have done so far, let me bring up the assignment number 6. So let me go here. Let me go here. Let me go here. Let me go. Oh, but did I tell you? Oh, yes, I gave you guys the combination of this and this, right? Right? Okay, good. So let me download this one. And let me open this up. Okay, so all right, so this question is a typical Hess's law question, just like very similar to what we did earlier. All right, so let's see if you guys can tell me what you would do in order to solve this problem. They gave you these equations and their corresponding enthalpy change values. And the question is asking for you to calculate delta H for this reaction here. So, any ideas? Let me hear what you think about this. The first equation. Okay, now why would you do that? Not saying you're right, not saying you're wrong. I just want to know your reasoning. Yeah, but there's no NH3 here. Remember, you're comparing each of these equations to this, right? There's no NH3 in this one. Now, in this case, you have NH3, right? But let's not deal with that yet. Let's deal with this first equation. What would you do to this first equation? When you compare this to this, what do you notice? Why would you multiply by 2? Exactly, because you have 4 NOs here, right? So as she correctly said, you multiply this by 2 so that you can get 4 NOs here, right? So when you multiply that by 2, you're going to get 2 N2 gas plus 2 O2 gas to give 4 NO. And that means, remember, that delta H for that will be multiplied by 2 as well. So 2 times minus 180.5 kilojoules. All right. Okay, what next? What about this equation, the second one? What would you do to that equation? Well, that's one thing you should do. Yes, I would agree that, but there's another thing that you need to do. Exactly. So there are 2 things you have to do to this equation. You have to multiply right through by 2 because you have a 4 in front of the NH3 in the first equation. But because the NH3 is on the left in this equation here, and it's on the right here, you need to also switch it, right? So when you switch it, so let me just put here, multiply by 2 and switch, right? So when you do that, you're going to get 4 NH3 gas to give 2 N2 gas plus 3 H2 gas. So what happens to the delta H in this case? Exactly. So this will be 2 times 91.8 kilojoules. You multiply by 2 and you change the sign from negative to positive. Very good. Okay. So that leaves us now with the third equation. What would you do to the third equation in order to, after comparing with the first equation here? Right, you have 6 H2s here. So what do you do to this? You're right, 6. You're absolutely right. Thank you. Thank you for that correction. Okay. So for the third equation, what should we do to that one? Multiply by 3. I totally agree with that. So you're going to end up with 6H2 plus gas plus 3O2 gas to give 6H2O gas. I just realized this should be gas as well. So what happens to the delta H value in this case? Multiply by 3. So 3 times minus 4, 83.6 kilojoules. And that's it. So we add them up and we cancel out common items on both sides. Okay, so what would be the common items that we can identify on both sides in this setup here? Nitrogen will cancel out. What else? Hydrogens, the 6 hydrogens here and here. Anything else? Well, they're common, but they're not on opposite sides. You see what I'm saying? You only cancel out those items that are on opposite sides. In fact, when it comes to items on the same side, you add them. You see what I'm saying? So let's write down what results. 4NH3 gas plus 5O2 gas to give 4NO gas plus 6H2O gas. And again, when you compare this equation here that you just derived to this equation, they're the same. So that means that the delta H value here, which is what the question is asking for, is when you add all these 3 values that we worked out here. So let me do that here. 2 times 180.5 negative plus 2 times 91.8 plus 3 times 4 is 3.6 negative. Okay, and according to my calculation, this works out to be equal to minus 1628.2 kilojoules. All right. Any questions? No questions? So if you understand this, let me clear this here.
Any difference in the next kilojoules per mole?
Yeah, sometimes they express the delta H as either one or the other. No difference really. I mean, literally, to be perfectly honest, it should be kilojoules per mole, but sometimes it, you know, in textbooks especially, they don't concern themselves with that. Okay, so if you understand number 9, then you should be able to do number 10, 11, and as far as the other part that I've added, the addendum for the same chapter, all these you're going to need the table that I talked about for all of these, because all of these, they're asking for you to calculate the enthalpy under standard conditions. All right. Okay, so what I want you guys to do now is try to do, going back to this one, try to do we just did number 9, so try to do number 10. Yes, sir. Mhm. Okay, so you have C2H4 here. I wouldn't change this. Yeah, I wouldn't change that because you have this on the left side, this on the left side, and it's one of them. So I wouldn't change that. Now for this one here, I would flip it.
So you want to change first one off?
I wouldn't change the first one, right?
Okay. So
Because if you look at this, it's on the left side, just like this one, and it's only one, the coefficient of one here. So, and that's one, so you don't need to change that. No, but this one now, you need to flip it because the C2H6 is on the right side. So you need to flip this, and therefore the sign is going to change. And then for this one here, the H2 here is on the left side, just like this. So I would leave this as it is. So the only one I would change would be the middle one. Mm. Yes, ma'am.
Question, are you able to divide? Like,
Oh, yes. Let me see this one here. So
do you have to divide the first one?
yes. So you can multiply this by half, which means that you multiply that by half. Yes, sir.
This one, is that 2H2 on the left side and 3 on this side? I have to switch it and then.
Well, if you look at this carefully, you see that not only do you have H2 here, but you have H2 here. So if you add these two together, you're going to get 3H2. Well, let me put it this way. If you have two substances in the same equation, I wouldn't worry about multiplying any of them by anything, right? I'll just move on to the next substance. So let me see what you have here. Okay, so, oh, you see, you have 3 hydrogens here, you have 2 here, you have 1 here, right? So I wouldn't even worry about the hydrogens yet. That will work out, but let me see here. So you have 2 ammonias here. So okay, so what I would suggest you do, because since you have 2 ammonias here, and you have 1 here, I would divide right through by 2, because you want, exactly, instead of multiply by 2, which means you have to divide this by 2 as well. And then as far as this equation is concerned, you have CH4 here on the right, but you have it on the left here. I would flip that. And then for this equation here, you have HCN here. Again, you have 1 here. So I would divide this by 2 to get 1 here. And then you're going to see when you add them up, it's going to work out to give you this equation here, because some of these hydrogens will cancel out each other. All right. Let me just make mention of something here since he asked this question. Let me go back to, hold on. In some cases, oh, I forgot. Let me share this. Where is it? What question was that again? 11, okay. So let's look at question 11. You'll notice in question 11, right? You have the same substance, hydrogen, being shared between these three equations right here, right? When you're faced with a situation like that, I would not worry about multiplying hydrogens by any number, right? Focus on the other substances, right? So like, for example, in this case here, you have two ammonias on the right side and you have one on the left, right? So what I would do is flip this around and divide by 2. In this case here, you have CH4 on the right, but in the original equation, it's on the left. So I would flip this around as well, right? In this case here, you have HCN on the right, but you have 2 here, and here you have 1, so I would divide by 2. But I wouldn't worry about the hydrogens, because what you're going to find out is that after you have made all those changes I suggest, when you add them up, some of the hydrogens will cancel out, and you're going to end up with 3H2 on the right side in the final product, in the final equation. So the point is, whenever you have the same substance being shared between different equations, don't focus on that. Focus on the others.
One.
Yeah, you want to have half N2, 3/2 H2, and NH3, right? And then you have to divide that by 2 as well.
I'm adding more, and the half hydrogen here would cancel out the half there.
Right,
and that
so-
would just have to be 3.
Exactly, and that's why you end up with a 3H2, right? Exactly. Mhm. Okay, oh, that's what, use a pencil. That's you're going to be using this equation kinetic energy is equal to half mv squared. The key thing is that the mass must be in kilograms and the velocity must be in meters per second. So you need to multiply by half. Excuse me. You did the right thing here, but now you need to multiply by this squared, 6.00 times 10 to the 5 meters per second squared. And when you work that out, the answer will be in joules. And then you can convert to calories and convert to kilojoules. Okay, so let me just say, or remind you that you'll be you guys should see the emails I sent you with your assignments, right? I did that this morning, so if you have not received it, let me know. But so your test, which will be next week this time, just to be sure, so that we're all on the same page, that would be based on chapters 3, 4, and 5. Chapters 3, 4, and 5. So chapter 6 will not be on it. All right, so you don't have to worry about that for now. And I'll be around today in my office from 2 to 5 if you have any questions. And I'll be available online on Skype tomorrow from, I think, the same time, 2 to 5. So feel free to contact me if you have any issues. You two take care.